Wonderful. Well, thank you guys so much for having me as part of your group today. It's a real honor to be able to share some of my experience and insight with you guys. I know that you've seen my long form video, so you probably know me as a biomechanical engineer studying how people move. I got into biomechanics because I was a competitive athlete. I was a freeride skier when I was in high school and college. And that was such a huge part of my life, and my body wasn't functioning really as well as I wanted it to. So I got interested in biomechanics and pursued that for a handful of years. But while I was in biomechanics, I started to recognize that I was more drawn to the technologies, the hardware, the sensors, the software that we were using. And because I wasn't competing as an athlete anymore, I wasn't as interested in the human body as I had been previously. So I actually just made a change this spring that's not reflected in my video. And I'm now a robotics engineer. So I want to share with you guys a little bit about my transition and some of the technologies and math and science concepts that overlap between biomechanics and robotics. In my new robotics role, it's not, I think, what a lot of people traditionally think of as robotics. We make agricultural equipment. So I make robots that harvest strawberries. They drive through the farm, they identify which berries are ripe, which ones we can reach, and then compute how do I take the arm and go and actually get that one and safely place it in a tray. I think so much of how robotics is presented at a middle school, high school, youth level is really like battle bots. I had no interest in robotics until a year or two ago. And so I really want to share that robotics can be used for good. There's so many applications outside of warehouses and conveyor belts and, you know, the battle bots that you see on TV. So yeah, that's where I'm at now. As I mentioned, I'm going to share a little bit about how biomechanics and robotics really leverage a lot of the same technologies in ways that you guys can present to your students. The first of that is using technologies, so sensors, embedded computers. Have any of you guys used Arduinos or Raspberry Pi in your classrooms? I see a few nods. This is really the advanced version of that. So anything from measuring somebody's joint angles while they're out in the field using sensors, inertial measurement units that are measuring motion, to cameras that are automatically computing, is that a strawberry, is that not a strawberry? And feeding that information to a microcomputer. So not necessarily your full laptop or desktop computer, but to a small chip that's then making a decision. What am I going to do with that information? Am I going to turn on a little red warning light that says, uh-oh, you're flexing your knee too far for your rehab program, like back off a little bit. Or you're generating too much force too soon after your surgery. So that's in a biomechanics context. In a robotics context, it's like, okay, you know, we know that the joint angle of that robotic arm is approaching its, you know, the programmed, the goal position. We want to slow down the motor as it reaches that position. And so having that feedback from sensors to a computer, and then use that feedback towards something like a motor or a light or some other output. All of that kind of stuff is things that you can do with, like I said, Arduino, Raspberry Pi, really easy introduction to computer programming, and applicable across so many different disciplines. The other kind of middle school level concept that I deal with a lot in both the biomechanics world and the robotics world is math, and especially trigonometry and geometry. If you think about, because we're meeting in a 2D environment, I'm going to keep this in 2 dimensions. But if you think about the body on an XY plane, so Y is going straight up and X is going straight out. I'm going to scoot over here so you guys can see my arm. If you imagine that my shoulder is at the origin and my arm right now my arm's a fixed length, so it's always going to be this long. If I move my shoulder, my elbow is always going to trace a line that's exactly that distance from the origin, right? So if I know the XY coordinate of my elbow, then I can compute what's the angle from my arm, you know, how far do I have to move that arm? And this is exactly the same if you imagine this is a robotic arm instead of a human arm. Okay, I need that joint to be in a certain position to go pick that item up off the ground. What position do I have to program the motor to go to? And kind of vice versa. If I know that I need the arm to be in this position, you know, how do I compute how far it went? Or if I know that the joint moved 20 degrees, where is the arm now? And then you can start stacking joints on top of each other. So you have the shoulder that moves, and then you also have the elbow. Now we all human intuitively know that I can't scratch my own elbow because my wrist has a limited range of motion, right? And my hand is shorter than my forearm. So no matter how I configure my arm, I can't reach my own elbow. Robots don't intuitively know that about themselves. And so when we're computing for a robot, like go get that item, we have to figure out, is it actually something that it can reach? And what different positions can that arm be in to get there? So it's all kind of backtracking through that geometry, that XY coordinate plane, computing, you know, what's the angle of this line from the current position to be able to get to that XY coordinate. So hopefully that covers kind of some basics of what robotics and biomechanics and the kind of the engineering concepts behind it. I'm happy to answer any questions about that. And Koshi, feel free to guide me in any further direction if you guys want more on that.
Oh, no, thanks. And I just put in the chat, actually, I love that example with the arm. I love the fact that you did that, because I think it just, at least for me, definitely not a robotics, you know, expert in any way, even school level. It just makes it so accessible, and it's also connected to life science and math and, you know, engineering, you know, and so forth. So I don't know. I mean, maybe it'd be good for the teachers here. Could you see even something as simple as using that example that Sarah just shared with us? Would that work in the classroom, or what else would it take? Or, you know, what other information would be useful to add on? Let's just use Sarah's time here to address how this could be translated to a classroom environment.
What I enjoyed was you took the complex and described it in a simple way where students could understand how you're using that math, that our body uses it naturally, but for artificial intelligence, we have to program each and every little bit of information. So I think it links why we study the body so effectively with computers and sensors and have to transfer that into artificial intelligence.
And Sarah, just on Monday when we were together, we actually spent a few minutes chatting about math. Math came up quite a lot, as there was a sense of frustration I got from the conversation that, you know, school math is so far removed from sort of sexy math that's used in, right, the real world, and in these exciting jobs that our kids could participate in. But unfortunately, as we are chained to syllabi and curriculum, that, but what I loved about what you say, that I immediately saw, well, if you're teaching about angles, the examples you give as to why you need to learn about angles, which can make all the difference for both the teacher and the student, can be anything, including, hey, if you get a job like Sarah Wilson, here's her video, guess what math she really needs to think about when she's doing this programming. You know, it comes down to the math that you guys are learning, because a robot can only do what we tell it to do.
Right.
So that's what came to my mind. Other thoughts?
I used examples like this in the classroom when dealing with coding. Actually, we because we were virtual this year, our entire robotics unit was all online, and we had to do things like program the robot to sense, as she was saying, when to, you know, how to vacuum the floor. Mm-hmm. So we did programs for robotic arms. And so that example just falls right along with it. And I love being able to attach a person to the example and not just my iRobot, you know, because the monetary idea of, you know, being able to sell this robot to somebody is not as enticing as seeing a real live person who's doing this job, doing this work to solve a real problem. So I love that. Project management also is another cross example. When we teach how to manage projects to solve a real life problem, it goes hand in hand with that.
So Sarah, let me also ask you, so one of the things I've heard, not just from this group of teachers, but just working with teachers, is again, I'm going to use the word sexy, right? What's sexy is robotics and coding. And so the teachers who already work with that, oh my gosh, they already have all of that good stuff going for them. But then teachers who are stuck doing things that I used to teach life science, physical science, and then there's math teachers, and they have pretty, rigid topics that you have to cover. If you remember, they probably haven't changed too much since when you were in middle school. It's pretty much the same. So what would you say to teachers who teach physical science and math and, earth and life science in terms of, teaching those topics, but how do we bridge it? Because we know from research and through anecdotal evidence that the students who get psyched by what they're learning in their middle school years in those classrooms are much more likely to go on and take the higher level STEM classes later on. How do we work with the curriculum, the syllabi that exist, but still add on enough kind of real world connection, which is what you're embodying, so that it really becomes engaging? Any thoughts that come to mind for you?
I think it's really important to figure out what the students in your classroom are passionate about. If you have a group of sports fans, then take the biomechanics route and look at joint angles, look at, how much force is too much force on the knee joint, or, you can't flex the knee that far without putting it into a danger zone. And to start connecting between those things that they're actually interested in and put the math or the science in a context that gets them a little bit more excited about it. I think that I have gotten where I have in my career because I figured out how to take my strength in math and science and apply it to the things that I care about. But to be able to backtrack that and say, oh, you want to be an athlete, then you really need to understand nutrition. You need to understand biomechanics. You need to understand kinesiology. Here's the life science approach to that. Or you're really interested in environmental sustainability. Farming is a huge area where we need to improve. We need to figure out how to use less water. We need to be able to grow in these more contained environments. And when we do that, we open the door to being able to use more technology to be able to approach that. So, connecting the application back to something that they are interested in. Does that answer that question sufficiently?
I think that's really good. And I love the way you put it, which is, it's almost like in my head when you said it, it's like concept mapping or backtracking. So if you take whatever your topic is, the nice thing, and also the sometimes challenge about real world that's dynamic and evolving in the 21st century, is it's messy, right? Mm-hmm. And of course, textbooks and curriculum and so forth have little bulleted lists of neat little topics, apparently not so messy. And yet we know that there is a connection between the two. So if you take something like Sarah's job in the video that we've all seen, kind of backtracking and breaking it down to some key components, because the chances are there's something about, geometry, there's something about estimation, there's something about algebra that's related. So it's almost just making a few of those explicit, and like you said, approaching it through the life science route or the mathematics route, whatever you're teaching. And just what we are as teachers is the connection makers, the bridge makers. And there's almost infinite numbers of bridges, but maybe just finding some that you're comfortable with and presenting it to students. That's how I see it. And I think that would be a really neat way, as we are working our way through, Sarah, lots of the other ambassadors' assets as well, and thinking about, well, how does that actually become a useful asset for a middle school teacher and student, right? That becomes part of the curriculum and not just kind of, an add-on on a Friday, when you just have 2 minutes to kill. So that's what we're trying to do over here. So I love that. I think that's something, I love that because it makes sense and it doesn't take too much time, and it's something that we can all do very easily. Let's have one or two last questions or comments for Sarah.
The big question that came up was, Sarah, where do you work?
I should have started with that. I currently work at Tortuga Ag Tech. It's a small agricultural startup based in Denver. I'll throw the link in the chat here. Oh, it looks like I accidentally sent it just to.
I'm pasting it in. That, yeah. I just did that. Okay. Yeah. So I just pasted in Sarah's response. Okay. It looks like it's coming from me, but she accidentally DM'd me. Okay.
Yeah. And I previously worked at a private research institute attached to an orthopedic sports medicine clinic. So we were working in conjunction with the orthopedic surgeons do some academic, kind of more academic context. I also see a question in the chat there about who encouraged me to make the switch from athlete to engineer. I had always been interested in math and science. I think every career that I explored as a kid was science related, but much more of it was ecology and naturalism. I wanted to be a marine biologist for a long time. I grew up in Colorado, landlocked state. The ocean was this totally foreign, like, oh, that's so cool. And then realized that I actually am a terrible swimmer and didn't enjoy salt water that much. And so my interests have changed a lot over the years, but it's always been math and science focused. When I was a competitive skier, I was hearing a lot of coaching that didn't seem to make sense for my body. It was very male dominant. This is how knees are supposed to work, and the feedback that I was getting didn't feel right. I was getting some coaching that when I tried to do those things, I was like, this really doesn't feel safe on my knee. I feel very uncomfortable with that motion pattern, and didn't feel like anyone truly understood how my joints were working. I was going through a lot of knee pain at the time. And so I got into biomechanics kind of from a selfish, why doesn't anybody know how this works perspective? Just trying to self-diagnose without going to medical school. But I had always had that math and science kind of engineering drive. It wasn't a career path that I really knew existed and sort of forged for myself. And it wasn't until a year and a half out of college that I realized that biomechanics was a thing that I could do, and went back to grad school for it. And so I love that you guys are now able to take the If Then collection and show girls and all kids that kind of no matter what it is that you're passionate about, there's a way to turn that into a career. There's a way to make that something that you want to pursue, and hopefully give them a leg up and not have to wait until 2 years after college to figure out how to get their career started and go back to grad school. So.
Last question for you, Sarah. I think there's one in the chat from Paige. You want to take that?
Yeah, the question is about pivoting between fields. I think that in science in particular, having experiences from a lot of different disciplines can help you approach a problem with a totally new perspective. And if you follow the straight and narrow down a certain career path, you're going to be thinking inside the box of that education and that career experience that you've had. Every time you change fields, so like jumping from biomechanics to robotics, I'm bringing in all of these different techniques and sensor technologies that are kind of the core of the biomechanics canon of how we do research. And now I'm able to apply them in a robotics context and come in with this like, hey, have we tried using this type of sensor? And everybody's like, oh no, we hadn't thought about that, because it's not part of the core robotics context. So I do think that jumping around a lot can really give you more depth and breadth to your experience, and can be really helpful for transitioning between industries. Now that said, going into academic research science may be a little bit more important to dive deep on something really specific and stick with it for a long time. I think that that's great for kids who are born knowing exactly what they want to do. I was not one of them. So yeah, I am 100% supportive of changing careers multiple times.
Thank you so much for your time today, Sarah. I think I speak for everyone. We're really grateful. I know how busy things always are for people. Thanks for taking the time to jump in and inform this group of educators a little bit more about what you do and your take on STEM and STEM education.